Okay, let's solve this second order linear DE using power series. We could solve this using Laplace transforms. We could not solve this as a homogeneous DE because it doesn't have constant coefficients, or at least it would be much harder. Notice it's second order, so we're going to have two free parameters. A0 and A1 are going to be free. We assume a power series solution of this form because our P of x here is 1. All points are ordinary points. We don't have any singular points, so we can expand this anywhere. We're going to expand it about x equals 0. So that assumes a solution that looks like this. Here's our first derivative, and here's our second derivative. Notice, just remember, we don't always want to play this game, but sometimes it helps. The first two terms here are both 0. If I plug in n equals 0 or n equals 1, so we might as well start counting this guy at 2. Notice I didn't do that with this guy because I've got this extra x that's going to multiply in there and it's going to fix my power problem. But I could have, it wouldn't have hurt. Okay, so plug second derivative, first derivative, and original back into the DE. Don't forget about that minus and that 2x. And we get this. Bring that 2x in. So x times x to the n minus 1 gets me up to x to the n. So these two sums here both have x to the n and they both start at 0. That makes me happy. This guy doesn't fit the pattern though. He starts at n equals 2 and his power doesn't match these guys. We need them all to match. So the easy way to do that is go, well, this needs to go up by 2, so this can go down by 2. Everything inside here will go up by 2. Even the AN right there, up by 2. This will go down by 2. Write out a few terms, starting at 2. Write out the first few terms of this. Write out the first few terms of this. Convince yourself that it's really the same sum. Now that all the powers match and all the starting points match, I can squish this together into one single sum. That's this. The only way that's possible to equal 0 is if every single term, every coefficient is 0. So we set all of this equal to 0. And we solve for an plus 2 in terms of an. So there's a little bit of arithmetic there. Move this over, factor out the an and divide, and I got this. So an plus 2 depends on an. Our first two coefficients are free. And now we start plugging in values for n, starting at 0. So remember, this is not telling me, when I plug this in, it's not going to tell me the A0 term. When I plug in n equals 3, that doesn't tell me A3. I'm plugging in on both sides. So when I plug in n equals 0, that gives me A2 is related to A0. And plug in 0 for all the n's. Plug in n equals 1. Write this down and try these on your own. Here's my A3 related back to A1. It's recursive. Plug in n equals 2. A4 relates back to A2, but we know A2. It's right here. So put that here and I get this. That, by the way, is 4 factorial. And so forth. We keep going. This is my y1. I really should have written it like this. Y1 is all of this. Y2 is all of this. Everything that has an A naught in it, we call Y1. Everything that has a A1 in it, we call Y2. Then our general solution is Y equals A naught Y1 plus A1 Y2. Let's use that to solve an initial value problem. So if I plug in y equals 0, all of these terms are 0, or y of 0, sorry. If I plug in x equals 0, all of these terms are 0, all of these are 0, we just get a naught. And that's what's always going to happen. Y of 0 is always a naught. So a naught must be 1. Try this on your own. If you take the derivative and set it equal to 0, once I take the derivative, all of these guys are going to go to 0 when I plug in 0. Derivative of 1 is 0. Derivative of all these guys is going to have an x left over. When I plug in 0, everything here will die. Y prime of 0 will just, or y1 prime of 0 will be 0. Y2 prime at 0 will be a1. So we get a0 was 1, a1 is 5. And that's always going to happen. Now let's use this particular solution to approximate y at 0.2. So y in general is a1 y1 plus, a0 y1. I wish we didn't mix up the numbers like that, but we do. Y is a0 y1 plus a1 y2. So now I'm just going to plug in 0.2 into all the terms that I bothered to write out. These terms keep getting smaller and smaller because we're raising to higher powers. So numbers close to 0 raised to a big power drop off pretty quickly. Especially, look, I got this 7 factorial here. So I could keep adding in extra terms, but they're going to drop off pretty quickly. So I typed this all into Wolfram Alpha and I got this.